bad people.
Okay, so let's see here. So we were doing this, right? I think what we were doing is we were finding the critical numbers for, what did we do? I gotta remember here. Oh, right. So what we did is we just took the, come on now. We took the sine 3x and expanded it, right? But then we never went back to the original second derivative function, right? So what we needed to do here, we turned sine 3x into this, right? Okay, so what we really needed to do here was take this guy. Is that a little blurry or is it just me? Is my old tired?
I think we need to fix the.
Yeah, I think the projector's, something's up with the projector.
I might have to have you work on that at the end of the period to get that fixed.
It looks fine, I think it's just your eyesight or whatever.
Serious? That could be too.
Calling him blind is a bad.
That could
worse
be
when you're closer.
very easily.
Yeah, it's probably a lot worse when you're closer up to it.
Yeah.
Here it looks fine.
Okay, so then this guy right here, this is just the expression, this expression right here goes there,
Oh.
right?
That doesn't.
That's all we did. Gross. Let's double check that, but I'm pretty sure that's right.
Yeah.
Because that's just sine 3x right there, right? So we expanded that all out and got that. Yep.
We solved that part.
Okay, so then we gotta go back here and,
So we need to put that into the.
yep, we gotta plug that back in there. So y double prime then is equal to negative sine x plus 1/2 sine x times 3 minus 4 sine squared x. So what could we do?
Well, that's pretty easy, take a sign out of everything.
Good, we could take, and let's take a 1/2 sine out of everything. Okay, so then that's gonna give us 1/2,
Negative or leave the negative?
we can just leave the negative, it's fine. So we just take the 1/2 sine x, and that's gonna leave us with a negative 2, right? Plus this stuff. Right? Everybody agree? Okay, which is equal to 1/2 sine x times 1 minus 4 sine squared x. Okay? So what are our zeros then? Our zeros are when this is equal to 0,
Then 1 minus 4 is.
when sine x equals 0, or sine squared x equals 1/4.
Yeah.
Agreed? Which is when sine x equals plus or minus 1/2. Okay? And so we get something fairly ugly here. We get lots of points.
Story of this classroom.
Yeah.
Got something really ugly.
So we get, if we look on the unit circle,
Do it right.
and we're just going from 0 to 2 pi, right?
Yeah.
So where is sine equal to plus or minus 1/2? That's the y coordinate, right? So that's gonna be there,
Pi over
there,
6, pi over
there.
6,
there, right?
7 pi over 6, and 11 pi over 6.
Actually, 7 pi over 6?
Yeah. And sine is 0, there, and there, right? Okay? So, wow, we get we get a big, big table. Big table. Okay, so what number is this, by the way?
What are the x values? It's
39.
You got a bunch of numbers for, oh no, we didn't.
Yeah, we get a
Pi over 6.
ton. So in our book, this is the, okay, it's 25 in ours. I'm just gonna check and make sure that this is as complicated as, see, make sure we haven't made some mistake somewhere. This is a pretty hard problem.
I'm assuming there's a reason they said use a graph.
Yes, there evidently is a reason. And yes, we are on the right track. Huh. How about that? Pi 6, 5, 6 pi, 7, 6 pi, 11, 6 pi. Yep, we're on the right track.
awesome.
This one is really, really, really a nasty one.
See,
But
Or the rest of these
how
just
good does
sit
it feel to
down.
just conquer it? A
No.
horribly nasty problem. It just feels awesome.
It feels great that you're conquering it.
See, at this point, I would just assume I would have done something wrong already, and that's.
Yeah.
Okay,
Because-
but honestly,
in the 3x
this
book.
is kind of the step you take between like first year calculus and second year calculus. It's just getting beyond that self-doubt, you know, and just being careful. It's amazing, you know, sure you can make mistakes, but you will be amazed as you get better at algebra and better at trig, and you know, you kind of start, and you just learn to be organized and careful in your work. You'll be amazed how often things just work out. I mean, I had that feeling a million times in college. It's like, there's no way this could be right. Holy crap, it's right. You know, it's if you have to go through pages and pages of algebra, and sometimes you'll find something that's not quite right, but then the trick is to go back and find it, and you know, once you've done all the work, you can do it.
Look through your research paper of work on it.
Yeah.
Exercise 9.
Okay, so let's just summarize, real quick, let's just summarize what we did here, right? Because this is a pretty nasty problem, and there is a reason that they told you to use a graphing calculator on this one, because this is,
So those ones. do
this
we
is a
have to
pretty
do
hard
this?
problem. Honestly, this would be a really hard college problem.
Can we
I mean,
cut
this
those
is-
out of the assignment then?
What's that?
The ones where it says the graphing part, can we just cut those out of the assignment?
That's like all the problems.
It does not.
Shh, Michelle. All of them except for the first four.
This one is actually not.
No, it is, but yeah, this is the only one I think you really need to use a
It
graphing
seems so
calculator.
easy when you go through it with us. It's just when we look at it by ourselves.
Well,
we're
it's
like,
the one,
"Eh."
the sketch of graph ones. That's the one I'm talking about.
And
Which
you
is
see
37, 39, and 41. Ooh, what did I get?
So what did we really do here, right? All we really did was, I mean, the hard part of this, you have to admit, the hard part of this was probably the trig that you were unfamiliar with, right? And so we know our trick now for finding like the cosine of 3x. We'll just make that x plus 2x, right? And use the angle sum formula, right? So really, I mean, the calculus wasn't very hard. It was just plugging in all that trig stuff that was more complicated. But when all the dust settled, remember that what we ended up getting for the first derivative was this, right? This
It
was our first
cosine
derivative.
x minus 1/6 cosine 3x.
It's right underneath that. It's the 5 plus 4 sine x.
Oh,
times
this-
cosine x.
Right, is what this became, right? So it became this times this factor.
Which we condensed.
We condensed this factor. Let's just look at our work here. We condensed this factor down to that, right? When we converted the cosine to a 1 minus sine squared and distributed the negative and added like terms, right? And so what that tells us then is this is y prime. Well, there is a 0, right? When cosine x equals 0, this yielded a 0, right? But this one did not, because it makes no sense. There are no real solutions to this, right? Even if we try to solve for sine x, well, sine squared x is negative 5/4, right? So that's not gonna work under any circumstances, right? That's not gonna give us a real solution. And so that one, this is the only critical number we got for the first derivative, okay? Then we went on and things got really ugly when we had to take the derivative, the second derivative, right? So the second derivative, first of all, we had to figure out what was sine 3x. So sine 3x was that, right? And then what? Oh, we found this was our second derivative. That was easy, but then we had to plug that in, right? That was the part that was complicated.
Just simplifying it.
Right. I mean, just turning that sine 3x into something in terms of trig functions of x was somewhat complicated. And that's what we ended up with. So when we plug that in, now we're just evaluating, we're setting the second derivative equal to 0 and solving. So we end up getting this relatively horrible function right here. Not horrible, I guess. But then when we set it equal to 0, we are going to get a bunch of critical numbers. We get sine x is 0 at, let's write them all down. When sine x is 0 at 0, pi, and 2 pi, right?
Yeah.
Okay. And then The other ones we get were where sine x equals plus or minus 1/2 from the zeros of this vector, right? And those would be pi 6,
7 by 6.
and what else, 11 pi 6?
Yeah.
Okay, so we get lots of critical numbers for that one, right? So then all we gotta do now is we've gotta go build our table, right?
Hell yeah.
And so, let's see, our table, we could even use this function right here if we want to. Yeah, I mean, we could go back and use this simpler version if we want to of the second derivative. Or we can use this one. Doesn't matter. So when we're gonna make our table and we have to use we have to evaluate the signs of the second derivatives using test points, we can use any version we want to. That's probably easier. We'll just use this one. Probably, yeah. Because it's a product of two factors. Yeah, that's probably easier. Okay, so we're gonna use this as our second derivative. It's gonna be y double prime equals 1/2 sine x times 1 minus 4 sine squared x. In our first derivative, we gotta go retrieve that from the first page. We never actually wrote that one all the way out. It was this times this, right?
1/6 cosine x.
Yeah, the 1/6 cosine x times that factor. So let's write that one down. So y prime equals 1/6 cosine x times 5 plus 4 sine squared x. So now let's just grab all this stuff and go to a new page and put it there and make our table, right? So we've got our original function, which is that guy. Okay, we never turned that in. I mean, that's fine. We leave it like that. So I'm just gonna do this on the keyboard.
So for what time, why do I have cosine x minus 1/6 cosine 3x?
Because that's what the first derivative is, but then to find the zeros, you have to do.
Oh, then
cosine
that's why you
3x.
had all that stuff. But I mean, that's.
Oops. Not that one.
Trust myself.
Yeah, I know, but yeah, I read.
That's yours.
No. No. Why would I trace it?
Why do you write the first one?
Because I hate writing in pencil. Makes me uncomfortable. I don't like being able to go back on what I did.
Oh, okay.
I feel like it's lying.
All right, so let's make our table. So then we got.
I put the 0 and 2 pi. So,
Wow.
So critical numbers. So what did we get? Critical numbers we got. What were they again? They were.
0.
We're going all the way from 0 up to 2 pi, and we had pi 6, 5 6 pi.
What about pi over 2 and 3/2 pi
Were those critical numbers?
for the first derivative?
yeah, pi over 2 3 pi.
They were for the first derivative?
Yeah.
Okay, so we need those.
Oh,
Oh no, we're still good. We're still good. We're still good. Don't worry, guys.
Pi over 2, 5 6 pi, pi. 7 6 pi, 3/2 pi, 11/6 pi, right? That's not, let me get the idea. I should have probably spread those out a little bit, but oh well. And then these were all zeros of second derivative. Smooth him over. Oh no, that was just a coefficient, wasn't it? Yeah. Okay, and then these were,
Wait, you were 2 pi to 0.
that's,
0 and 2 pi.
oh, yeah. Okay, well, and those are endpoints, so it doesn't really probably matter, but.
But we can't
But
put
it's a
those there.
table.
It makes it a little.
Filling in the table.
Makes it look like we've done more work.
There you go.
On pi, you guys
And
just
so
have
pi
tables
halves
and
and 3/2 pi were the only zeros for the, that's right, for the first derivative.
Well, and
Okay.
0.
No.
No.
I don't think so.
But cosine x.
Cosine is 0 at the top and the bottom.
Oh, yeah.
Okay, so then, now we just gotta pick test points, right? So we're gonna pick, boy, that's gonna be weird test points, aren't they? So we're gonna get test points like at pi thirds. 2/3 pi, 4/3 pi,
Can't we just use the,
whoops,
Well,
wrong
it's not
place.
close enough to use the test points.
yeah, can't we just use the second derivative 0 as its test point to the first derivative and vice versa?
No, because we need to see the slope.
Right.
Oh.
We need to, we have to work in the bottom row, so we can use this one. That one's gonna work and that one's gonna work. So I guess we wouldn't need those, would we?
No.
Right. So we can get rid of
Oh,
those.
good thing I wrote it down.
It is not your day-to-day, River.
But we are gonna need a test point
Copy off the video.
there, which is really inconvenient, because that's not even on the unit circle, right?
Oh, so how do you make that?
So, well, we'll just have to use our noggins on that one a little bit, right? And just
Or
know,
we
just
can use
know by
our
the
graphing
quadrants what the
calculator.
behavior is.
Can't we use our graphing calculator on this one so we can see the slopes of it?
So we'll make this like what, let's say it'd be like 11/12 pi,
11, 12,
and this one will be 13/12 pi. And then we can use this guy in between those two. And then here we'd have to do something like, what, 23/12? Something like that. Okay? All right, so now let's evaluate signs of these things. So what is the sign of the second derivative at pi halves? So at pi halves, we're gonna get positive times negative, right? In fact, that's always gonna be negative, isn't it? Well, not always, I guess, but for us it will be here, because sine pi halves is gonna be +1, so positive times negative is negative. So that gives us a negative. So this is a, it's gonna be a maximum,
Concave
oh,
something.
right?
That.
What about this guy? 3/2 pi, we're gonna get negative times negative is positive, right?
Yeah.
Okay, which is gonna give us a minimum,
Yeah.
okay?
Nice.
And now we just gotta see what's going on in between all those places, so.
Would
So
we just
let's
use
see.
our calculator to put in?
Yeah, we could. So, but we don't even probably need to. We just know this is gonna be, if I look at the sign of this thing, of the second derivative, so what's the sign of 11/12 pi gonna be like?
gonna be negative.
It's gonna be very big and positive, right? So we could, does that make sense? It's gonna be bigger than the square root of 3/2, right? So say 0.9, right? Something like that, so the sign. So the sine squared is gonna be something like, it's gonna be something still pretty big,
Yeah.
right? So we could say like, 0.8, but we can see pretty clearly here that this is gonna end up being negative, isn't it? Right? This is gonna be positive, and so we're gonna get negative there. Agreed? So is that a point of inflection?
No.
No, it's not. Did I go to the right place?
But
11, 12, oh no, hang on, I didn't.
that wasn't the test point anyway.
That's the wrong place. Yeah, the 11/12 is gonna be very close to pi, so it's gonna be very small.
Okay, that's what I was like, wait.
Right, right. Does that make sense? It's gonna be something like, if we look at the unit circle, 11/12 pi is way down there, right?
Yeah.
It's still positive though.
It's gonna be, it's gonna be positive, but look what we're gonna get here then. This is gonna be 1 minus 4 times a really tiny number, right?
So it's gonna be positive.
So it's gonna be positive. Yeah, so that's gonna be positive. So that is an inflection point.
Okay.
It's a point of transition.
Yeah.
What about 13/12? At 13/12, we're gonna get something like right there. So we're gonna get a very small negative number for sign. Agreed? See how we're doing this? And so that's gonna give us, over here it's being squared, so it's insensitive to the sign anyway, right? So that term is still gonna be positive, but this one is now gonna be negative, right?
That's gonna be negative.
Everybody with me?
Yeah.
So that makes that negative, so we get another inflection point, okay? And another one. And then you can kind of see the pattern here probably. What are we gonna get here? 23/12 is gonna be down here, right?
Yeah.
That's still just gonna be the same.
So that's gonna be the same result as that guy, isn't it? It's gonna be minus. And then if we go down here and do like pi 12ths, it's gonna be positive.
Wait, why? Oh.
Because we're gonna get positive times 1 minus a really small number, so positive times positive.
It's a lot of inflection points.
Yeah, it is. That's a lot of inflection points.
Wait,
So-
so for 23 pi over 12,
But
you should, why is that negative?
that's negative because that's gonna be the point right there.
Okay.
So the sign of that is really small and negative,
Yeah.
right? So that's gonna give us negative minus 4 times something small and negative squared is something really small and positive. So 1 minus, something really tiny is 1,
Yeah.
just like it's gonna be positive. So I get negative times positive is negative, okay? Right? And so that's our picture. We could graph that thing, but man, I don't really want to.
So does that mean?
That's the whole point of the
Does that
problem,
mean we
is
don't
sketch
have
a
to
graph
either?
of the function.
Well, maybe we better.
Wait,
Okay, so we'd have to
it's a-
anchor this thing, so our original function, if we go back and let's just find some key points. Let's find the coordinates of the maximum and minimum, right? So the maximum is gonna be at 1/2, what do we get out of this thing? So we're gonna get sine of 1/2 is 1, right? And then sine of 3 times pi halves is gonna be 3/2, so that's -1, right? Times -1/18, so it's gonna be just a little bit less than 1. 17/18. Okay. So there's 1 point. What are we gonna get at 3/2? You get -1 minus 1/18 times the sine of 9/2 pi. Well, 9/2 pi, you can see that's gonna be, 9/2 is 4.5, right? So we're gonna go around twice and then go up to the top again, right? So that's gonna be -1 plus 1/18, so it's gonna be -17/18, right? Make sense? Here's something we could do to make life a little bit easier. If f of x, and this is actually a pretty big deal, if f of x equals sine x minus 1/18, oops, sine 3x, what can you tell me about the symmetry of this function?
It's like you over the y-axis. Or symmetrical. Oh, it's the same thing, because sine is one of the special ones.
Agreed?
So
So is sine odd or even?
It's odd.
It's odd, right? So the sine of negative x equals negative sine x. Agreed? Everybody with me? Okay. So then this just becomes negative sine x plus 1/18 sine 3x, which is equal to negative f of x, right? So this function as a whole is odd, isn't it?
Why do we need to know that?
Because if we know that it's an odd function, then let's see here. Oh yeah, why do we need to?
Because it doesn't go into, X is never negative.
Yeah, you're right.
Yeah.
I guess we don't need to. Let's see.
It's like,
Always like,
Yeah,
oh,
we
I
don't.
don't reason.
Yeah, never mind. Thought I had a reason, but I didn't.
Okay.
Never mind. So that didn't help us very much. Let's get rid of that, Jim.
Someone actually called.
I do not write that one down.
There is a way you could make that work actually, but I'm not gonna break you through it. We could phase
Oh, we
shift
got
it.
time, we got time, go.
We got 14 minutes and I still want to ask another question.
We could phase shift the whole function and show that it's insensitive to phase shift, and then that proves that it does actually have odd symmetry about the middle. But I wouldn't.
That's what I said to begin with. Nailed it.
Okay, so then all we'd have to do, and then we know at pi, what do we get? At pi, we're gonna get 0, right?
and when we get 0 at 2 pi,
Yep.
how many pi's?
And there, we're gonna get 0, and there, we're gonna get 0. So that would be enough to graph this thing, right? So now if we wanted to sketch this bad boy, wow, this was a major league problem, huh? So we're gonna go, so we know that we're gonna have, let's see, halfway through this thing, so at pi, we're gonna be at 0, right? At 0, we're at 0, and at 2 pi, we're at 0. And here, we're gonna be up. Here, we're gonna be down. And then we just gotta add these points of inflection in there, right? So we're gonna have positive concavity up to pi 6. So if that's pi halves, that's gonna be like 1/3 of the way there. So it's gonna look kind of like this, and then it's gonna go negative concavity all the way up to 5/6 pi. So right there, it's gonna go like this, right? And then starting about there, it's gonna turn negative again, or positive again, right? Up to pi. So it's gonna go like that,
It's a normal sign.
and then it's gonna go down again till we, see what I'm saying? Till we get up to 3/2 pi, all the way up to 11/6, right? So then clear down here, it's gonna go like this. It's gonna go like that, and then it's gonna flip and go like that, and then it's gonna flip and go like that.
So it's like a sign here.
Kind of, like a
It's
modified, I
kinda
mean,
like
sort of,
wiggly, sine curves.
right? Does that make sense?
Probably did all that.
Now, can
Yeah,
you-
sheesh.
can you
Wow,
graph
that was a lot. Admittedly, that was a lot of work. Why don't you guys just, we won't count that one about.
What about the other ones that are probably exactly like?
No, they're not. Let's go look at some other ones.
Can we do
Pretty sure.
5, please?
Yeah,
Wait,
Whew.
graph this.
That is 2 full pages of stuff.
that's a lot of stuff.
Almost 2 full
I think
periods
I
of
did
it
half
too.
page.
That's a lot of stuff.
So some difference to do, because Vetnetsky to evaluate. How come we don't have teachers come, or like Vetnetsky or Jerome coming in to evaluate this class?
Cause this stuff's way over their heads. He could be talking about like nonsense.
Well, I
we
wanted to
wouldn't
see
know.
them, like, I don't know.
It'd be kind of fun to watch them try to follow.
I came here and evaluated this class.
Did you?
I did. Yeah, no.
That's,
I remember
you know-
when I remember when you came in.
different animal.
Oh,
We should
wait.
just do some nice relaxing like geometry or something.
Yeah.
Just, like,
No, no,
have
no.
a sauna
No.
day where we just do geometry.
No,
and
not
all that stuff.
geometry. We want like 5th grade math.
Oh,
Like
God.
a speed
Yeah,
multiplication.
speed
Yeah,
multiplication
boy, you don't
tables.
We
die.
can do like the multiplication tables and
Do you
stuff.
know
That's
those-
math is
those-
boring.
We kill our brains so
I remember when she
much.
We don't need
I remember those
brain
pepper
cells.
lunches.
No, we don't. No, we don't.
Yeah, you guys, here's the thing. You guys got to be, you're doing exactly the right thing because you got to take maximum advantage of this time in your life when your brain growth is so rapid. You got to just be thinking really hard all the time. That's.
Sometimes my brain doesn't catch up with.
No,
with
oh, trust me,
It's like,
it's
impressed
like-
how much-
Okay, Michelle, which one are we looking at here?
Like, my second derivative, I don't know. I got like
I got.
Which one though again?
35.
35.
Yeah, my second
Okay.
derivative, I'm not sure.
Ah, that's a good one to look at.
Did you get any derivatives? I didn't get any
I
derivatives.
got derivatives.
Yeah,
What's the derivative? No, I mean like the zeros.
Oh, no critical numbers.
I didn't get it.
Okay, yeah, this is a good one. This is a good one to look at. So,
In 10 minutes.
yeah, I think this could be a 10-minute problem. I mean, I'm really bad with
10
time.
minutes start to the problem.
I'm really bad with time, as you've noticed. I don't really always.
That's why we should discuss the.
I'm fairly optimistic about time usually.
3 minutes, we've got enough time for this.
Sure. Okay, so how are we gonna rewrite this? So we could rewrite this. We could make the bottom a 1/2 power, right? Or we could write it as a product if we want to. So we do that. Let's do something different, and let's write this as negative 2x times the quantity x squared plus 7 to the minus 1/2. How about? Okay. All right. So what's our domain?
All reals.
All reals is correct. Okay, all reals.
All reals.
So let's do our derivative then. So f prime is just going to equal. So we're going to get negative 2x times the derivative of the second one. So that's going to be what?
Negative
Times.
x squared plus 7 to the negative
Times.
2x. Wait, there's more?
Is there a reason you changed it into a product, like?
No,
lowering the-
no. They're perfectly equivalent. You don't have to do it that way.
So the end should be the same. the
Yeah.
first
Oh
one
yeah.
is-
Yeah. We'll get the same either way.
Okay.
Okay. Plus. Sometimes people prefer the product. The only advantage I can see to it is you don't have to worry about whether that's plus or minus in the middle. You know, that's the only practical advantage. So plus, then we've got second one, x squared plus 7 to the minus 1/2 times
Negative 2.
-2. Okay, good. So what can we do? Positive, negative times negative is
Take out a negative
positive.
3/2 x squared plus
Not that far.
the.
Wait.
Okay.
Okay, then
Or,
take
well,
No, we're good. You're on the right track. Now we can factor out we have like bases. What's the power of our base that we would factor out?
Negative 1/2.
No, negative 3/2.
Negative 3/2.
Because you want the smaller one.
We have to take the smaller of the two,
Oh.
okay?
I did this one
I did
individually,
it right,
so-
y'all.
So we could pull out then, we could take out, how about if we take out a 2 while we're at it? So we're gonna take out a 2 times the quantity x squared plus 7
Why
to
don't
the
we take
negative.
-2 out of it?
Well, we could, but we'd rather have our first term be positive maybe, right? And so we end up with what on this side then? All we're left with is x
2x.
squared, right, because we took out the 2, minus, what?
Just x squared plus 7.
X squared plus 7, to the 1, right?
Wait.
Because math and stuff. You learn about it.
Oh, I took out a negative, and so I don't have a minus.
Okay, but your first term would be negative.
No, I didn't, no, wait. No, I did.
Wait, so.
They have to be different signs, the 2 have to be different signs.
They are, my first term is.
Negative? Okay, that's fine. So then if we simplify this, the x squareds are gonna cancel, and I'm gonna get a negative 7 on top, times 2 is 14 on top, agreed? And on the bottom, we're just gonna get, yeah, x squared plus 7 to the 3/2. So do we have any first derivative critical numbers? No, we do not. Okay, so now we're on to the second derivative. Okay, before we go on though, for example, Michelle, you did this with quotient rule.
Yeah.
Okay, and that's fine. If you do this with quotient rule,
Takes more time.
well, it may be a tiny bit, but on the bottom, you're gonna end up just getting an x squared plus 7 to the 1, right? Now on the top, you would have had different powers. You would have had your base to the 1/2 and then to the minus 1/2. Right. Agreed? Right, and then when you factored that out, you would have factored out your base to the minus 1/2 coupled with the x squared plus 7 on the bottom is the same thing. Agreed? Okay. All right, so now moving on.
I got that answer, it's the second derivative.
That was weird. Okay.
Yeah.
Okay, so let's try the second derivative.
And are we gonna do power rule again?
Well, no, we don't. We don't because we have a constant on top. So we would always rewrite this as negative 14 times our base to the negative 3/2. You don't want to use either one, it's overkill, right? We just have a constant times a negative exponent, right? So it's simply power rule. Agreed? Okay, so then we end up with, and maybe we should just quickly
Wait, so
write
you
it.
don't use quotient rule?
No, absolutely not. You don't, because remember, you never use quotient rule. It would work theoretically, but it's a lot of extra work. I would just rewrite this as negative 14 times my base to the negative 3/2. All I need is just power rule, right? See what I'm saying?
Okay, and you can just use the chain rule because it's.
Yeah, that's all it is. It's just a power rule, a chain rule, power rule problem, right?
That's fine.
Okay, and that's, we haven't done that in a while, but you might remember me really harping on that. Whenever we have a constant on top, we would never use quotient rule. We always bring the denominator up to a negative power, right? It makes it much easier. So now what do we get here? Positive 21 times x squared plus 7 to the, good, negative 5/2 times
How'd you get a positive?
negative 3/2 times negative 14,
If you do the,
Okay.
right? And then times by the chain
2x.
rule, 2x.
I waited the times things still variant,
So we're gonna get
so you get 42.
42x over x squared plus 7 to the 5/2. So we do get a second derivative critical number at 0. Yeah. So when we make our table then, we can actually, I bet we're gonna finish this. We're gonna be real close. No.
3
We have
minutes.
to graph it still.
Oh, graph will be piece of cake.
There you go.
So all reals
One of like
is our domain. We had one critical number
0.
at 0, which was a 0 of the second derivative, so let's just try critical numbers at negative 10 and 10 or something, right? Doesn't make any difference. The bottom's always positive. What's the top's gonna be negative here, right? Positive here. So it is an inflection point. Okay, where does our inflection point live? Our inflection point lives at 0, 0, right? So this is a pretty simple one, right? One other thing we could do though, that maybe isn't quite as simple, if we take our function, let's just go to the next page. We gotta know the end behavior, right? Okay, so let's take our limits. What's the limit here? We gotta go back, and we haven't done this in a little while. The limit of our function, negative 2x over square root of x squared plus 7, as x approaches plus or minus infinity in that order. What's the ratio of our leading terms this time? We get negative 2x, but if I look at,
Isn't it just negative 2? Did it approach negative 2?
but what's that equal
That's my
to?
vote.
What's the square root of x squared?
Isn't that
Wouldn't that
the
just be
Absolute value, right? So in the limits, this is actually equal to, if we're on the tails of the function, we can just rewrite this as the limit of negative 2x over absolute value of x, right? And so that's gonna be when x is positive. When x is positive, that's gonna give us 1, isn't it? Right? So our answer is gonna be negative or plus 2. When x is positive, this part is positive 1 times negative 2, right? When x is negative, we're gonna get negative 1 times negative 2 is positive 2. Agreed? So then if we go back to our table, that's really useful. We get negative 2 there, positive 2 there. Now we can make our graph. Right, so we end up with this asymptote and this asymptote, and we're just gonna get like this, right? I agree. Hey, I did the same. Wow, that's a lot of math jammed into one period, huh?